Welcome everyone to today's CMCC lecture. My name is Ronan Academ. I'm a researcher here at the CMCC in Italy. I will be moderating today's lecture. I'm very glad to say we are joined today by Antonietta Capotondi, a senior scientist at the University of Colorado and the NOAA Physical Sciences Laboratory. Today we'll be hearing about the rhythms of the Pacific, touching themes such as decadal variability and ocean extremes. Later on, we will be joined by a senior research associate at the CMCC, an expert on risk assessments and climate policy, Anna Pirani, to help us with some interdisciplinary discussion. Before we begin today's lecture and I introduce Antonietta, I would like to first of all briefly introduce the CMCC, the host of today's lecture. The CMCC is a leading research center based in Italy, which focuses on the understanding the interaction between climate change and society. We are part of a much larger network. The CMCC interacts with intergovernmental panels, organizations, both internationally and nationally, and contributes to a range of collaborations with universities and other products and service providers across the globe. Our mission is to move from models of the climate to solutions, and we do this in three ways. First of all, by advancing climate research through multidisciplinary analyses. Second, by combining climate modeling with impact assessments and environmental economics. And lastly, by supporting science-driven adaptation and mitigation actions. Our research infrastructure is composed of 3 research institutes, strategic programs which help us ensure we provide that multidisciplinarity in our mission statement. We have a computing infrastructure and 2 specialized centers on digital innovation and high-level education and training. The 3 research institutes are, first of all, the Institute for Earth System Predictions, in which we work on climate modeling and predictive tools. Secondly, we have the Institute for Climate Resilience, which is a transdisciplinary research institute at the intersection of climate, ecosystems, and society. And finally, we have the European Institute on Economics and the Environment, which is at the intersection between environment, technology, and the economy. And these 3 institutes all contribute to different strategic programs within the CMCC. We are focused particularly on the integration of planetary, biogeochemical, and industrial carbon cycle into the modeling chain, a focus on the global coast, integrating AI and ML into the modeling chain, and also predicting socio-economic outcomes in a changing climate. As mentioned earlier, we have a range of facilities which aid us to go beyond scientific research. We have a high-performance computing center, one of the most advanced in Europe, which is fully dedicated to climate change research. We have the Advanced Digital Innovation Center and the Advanced Training and Education Center. Today's lecture is one of several lectures which have begun recently and continue into the future. So please scan the QR code if you want to see previous lectures, and be prepared to sign up for lectures coming up in the next few weeks. Here are the next 3 coming up, touching everything from 2-week forecasting, modeling wildfires, and link between temperature health and adaptation. So again, you can scan the QR code or visit our website to see the full schedule and register for these upcoming lectures. A few practical notes for today's lecture. Your audio and video are deactivated by default. And when it comes to the questions at the end of the talk by Antonietta Capotondi, you can write them down in the Q&A section. and we will get to them. So without further ado, let me introduce our speaker for today, Antonietta Capotondi, who is a senior scientist at the University of Colorado and a physical sciences laboratory at NOAA. Recently, she has also become a Bassi Fellow at the CMCC, and I'm very glad to say she is joining us here in Bologna for 2 months. Her expertise is on large-scale ocean circulation, climate extremes, in particular El Niño Southern Oscillation and the role of decadal and seasonal variability in the Pacific Ocean. More recently, she's become a leading expert on marine heat waves, and her current interest includes subsurface marine heat waves, and we will hear a bit about that today in the talk entitled Rhythms of the Pacific, Unraveling Decadal Variability and Ocean Extremes. So Antonietta, I will stop sharing my screen and leave the floor to you. Thank you so much for being with us today.
Thank you. Oops. Oops, sorry. Okay. Well, thank you so much, Ronan, for for the introduction. And sorry, let me go back to my screen. And thank you, everybody, for joining today. So, as Ronan mentioned, we are going to talk today about the climate variability in the Pacific, with focus on decadal timescales and also ocean extremes. So the Pacific has a rich spectrum of variability at different timescales. So first of all, in the tropical Pacific, it hosts the El Niño Southern Oscillation, which is the dominant mode of variability at interannual timescales with anomalies that oscillates approximately from positive to negative every 2 to 7 years. In addition, we also have decadal Pacific variability. So a typical pattern is shown here in the middle panel. Decadal variability has large anomalies in the Northeast Pacific, in the subtropic, especially in the Northern Hemisphere. But also you can see that there's an anomaly, I don't know if you can see my mouse, along the equator, which are reminiscent of ENSO variability. However, they tend to be larger in the Central Pacific rather than in the Eastern Pacific. And also you can notice that the meridional scale of the anomaly is larger. So variability is ENSO-like, so reminiscent of ENSO, but not exactly the same. And then, in addition, we have long-term trends. So trends, of course, the pattern of the trends varies depending on the period that we consider. So here is an example of a linear trend over the period, over the last 40 years, 1979 to 2020. And we see enhanced trends in the western part of the basin, especially in the mid-latitude and the North Pacific in the area of the Kuroshio current, but in the tropic, we actually notice that there is this large area in the Eastern Pacific where the trends are much muted or even slightly negative. And so this is in fact, so trends, detecting what the trends are is an important area of the research. So climate models exhibit different trends in the tropical Pacific, and so it is unclear if what we are seeing is really due just to anthropogenic forcing or also can reflect some aspect of internal variability like decadal variability. So all these time scales are important, and I hope to convey during this presentation that they are not disjoint, but they can interact to each other. So it would be very important to predict all of these time scales, and as advocated, in fact, in by a recent paper led by Jerry Mill, where he was advocating for this seamless prediction system from subseasonal to decadal and to future projection. So in this in this vision of this seamless prediction system, the decadal timescale play a very critical role. First of all, they have been recently identified as critical for near-term decision-making and planning. Also, they lie at the intersection between this interannual variation associated with ENSO and the longer timescales. In particular, in the tropical Pacific, they are particularly important in the tropical Pacific, where ENSO occurs, so they can modulate ENSO, as we will see, but they also can affect the longer term trends. So understanding the mechanism of Pacific decadal variability is really important, both for understanding ENSO, but also for getting a better understanding of climate change. So what I would like to do during the rest of my talk is start by providing an historical perspective on Pacific decadal variability and its societal importance, review oceanic mechanisms proposed for the tropical component of decadal variability, which it's particularly relevant for the full basin variability, and discuss also our current understanding of these mechanisms. And then discuss the critical role of tropical-extratropical interaction for the origin of decadal timescales and also the influence of this decadal variability on Northeast Pacific marine heat waves. So starting with the historical perspective, so in the mid to late 1970, the Pacific experienced this very dramatic change, that was associated with changes in several important quantities that were so abrupt and so profound that this transition was remained known as the 1976-77 climate shift. So these climate events really spared a lot of research on decadal variability and led in 1970 to the definition of the Pacific Decadal Oscillation by Nate Mantua. So this is the way the Pacific Decadal Oscillation was defined was in a statistical way using an empirical orthogonal function analysis. So it means that really it gives us the dominant pattern of variance. It is disjoint for any mechanistic understanding. So the pattern of the PDO that is shown here on the top left is similar to what we have seen before. And also, in this paper was also highlighted how it can be ENSO-like along the equator. But an important aspect of this paper is that it pointed out the strong connection between the evolution of this Pacific decadal oscillation, which is shown in the top right, with salmon production. So in the Gulf of Alaska, in different stations in the Gulf of Alaska, as you can see by the blue shading, periods of negative PDO are associated with low salmon landing, while during phases of positive PDO, there was a higher salmon production. The opposite occurred, the opposite relationship is found further south along the Washington, Oregon, and California coast, where the relationship was different. An aspect which I don't think is fully understood to date, but really gives a very important, shows us a very important and tangible effect of these decadal variations. Also, Pacific decadal variability impacts precipitation over the US, in fact, impact long-lasting drought events known as mega drought. One of the most iconic events that happened in the US was the Dust Bowl of the 1930s, which this long-lasting low precipitation condition were actually associated with persistent cold anomaly in the Pacific. And this relationship is also found in climate model. This is an example for one of the CMIP3 model, where dry condition along the US, shown by this brown color of a land, tend to be associated with the negative sea surface temperature anomaly over the Pacific Ocean, with different expressions, of course. There are other impacts of Pacific decadal variability. It has been associated with changes in the onset of springs to shift in the relative, population of sardines and anchovies. And as we will see in more detail later, also it has recently been associated with an increased likelihood of marine heat waves in the Northeast Pacific. So in particular, in the tropical Pacific, decadal variability is important because it can modulate ENSO. So what we see in this curve on the right side, so this is this index of this tropical Pacific decadal variability, so the component in the tropics, as a function of time, with time moving upward. So we can see that during periods like this period from 1977 to 1999, where the index was primarily positive, we see that more red. So on the left side, we actually have sea surface temperature in a thin band along the equator, shown as a function of longitude. So we see the sea surface temperature along the equator as a function of time. So during this period of predominantly positive TPDV, we see more red in this area, so we have more enhanced El Niño activity, so the positive phase of ENSO. And also these are very strong El Niños, so like the 1982-83 and 97-98, those were some of the largest El Niño on record. On the other hand, during phases of negative TPDV, we see more blue, so there are more colder conditions, more La Niña type activity. And also the El Niño events that we see, these red lines, tend to be weaker than during the positive phase. So there is this modulation of ENSO characteristics, and since ENSO can affect climate globally, that also can, this modulation can also be important for the global climate. Another important aspect of decadal variability in the tropical Pacific is associated to the modulation of globally average surface temperature trends. And this result is from a very nice paper by Kosaka and Shi. So in this plot, we can see that the black line shows the globally average surface temperature. So we can see that starting kind of in the 1960s, we see an increase in the surface temperature approximately to the end of the 1990s. And then starting approximately around 2000, we see a plateauing of this surface temperature anomalies. And this has been known as the global warming hiatus, which was highly politicized because was used by climate change denier as a manifestation of the fact that climate change may not be real. So if we take climate models and we just let the model run freely without, according to their own internal dynamics, with prescribed radiative forcing, we find this blue line. So we actually have a continuing increasing trend. However, in this study, what they did, they constrained the model to follow the observed sea surface temperature, which were colder in the eastern equatorial Pacific. And when they do that, also the model showed this plateauing of the globally average surface temperature. So providing really a good demonstration of how low frequency sea surface temperature anomaly in the eastern tropical Pacific can have a large impact on the global climate. So this cold phase of the tropical Pacific after 2000 has, of course, received a lot of attention. And how does it look like? So here I'm actually detrending the data. So we're just trying to look at only at the internal variability and looking at the differences of temperature differences between like 15 years after the 2000 and 15 years before. So we see that the change looks very similar to what we have seen before for decadal variability. So this is a kind of another representation of this decadal variability with large anomaly in the Northeast Pacific and then in the subtropics from the coast of California toward the equator. And then we have also cold anomaly along the equator. These sea surface temperature differences are associated also with changes in the atmospheric circulation. So what we see here in the bottom panel, the shading shows sea level pressure, and the arrow shows surface winds. So we can see that there are large sea level pressure anomalies, especially in mid-latitude, with positive anomaly, and then we see some negative further north. But this anomaly also have a tropical component, and they are actually able to, and they are associated within the tropics to this enhanced easterly winds that blow from east to west, and that reinforce the climatological trade winds. So we have, during the second period, we have stronger winds in the tropics, along the equator, which can move water toward the western part of the Pacific, and we can expect to have enhanced sea level in that area. Indeed, if we look at the differences in the sea surface height, so it's the dynamical component of sea level, we do in fact see this enhanced sea surface height anomaly in the Western Pacific and reduced anomaly in the Eastern Pacific. Now, sea surface height is dynamically linked to the upper ocean heat content. So when we see this large sea surface height anomaly, we can expect an increase in oceanic heat content. And we can actually check for that. And what we see here is the temperature averaged west of the dateline and then shown as a function of latitude and depth. And we see these very large anomalies, which are not at the surface, but they actually are in the subsurface. And they are kind of concentrated or near these lines, these isotherms, lines of constant temperature, which define what is called the thermocline. So this layer of the ocean that separates the warmer and more active surface layer with the more colder and quiescent deeper ocean. So this seems to tell us that the Western tropical Pacific acts as a heat reservoir and is able to sequestering heat away from the surface, and perhaps it could have partly contributed to this apparent slowdown of global warming. So there is just a redistribution of heat between the surface and the subsurface, the atmosphere and the ocean. So apart from its dynamical meaning, sea surface height and sea level are extremely important also for from a societal viewpoint. In particular, in the Western Pacific, we have a lot of islands, and so the sea level is very important for the population in these islands. And we see this is computed by from a paper by Merrifield in 2011, and is the trend over the altimeter area. So it's actually derived from satellite data over 1993 to 2010. So all of these islands are actually equipped with tide gauges. So they have measurements of sea level that go back several decades. And in this study, what they did, they averaged the time series across all of these time gauges and found the figure that is here on the bottom that shows the evolution of the sea level as a function of time. And it's very interesting to note that starting around maybe the mid-1990s, we have this very rapid increase in sea level in this region. Which again is a big open question. It's unclear to what degree it's affected by the decadal variability that we see similar to what we see on the left, or could also have an imprint of climate change and then be a manifestation of sea level rise. So What we've seen so far is that these decadal variations are associated with profound changes in ocean condition in the tropics. And so what are the leading processes that are responsible for these changes? So it is useful to just take a look for a moment at what is the climatology of the tropical Pacific and what are the main winds and currents associated to in this area. So the top panel shows the surface layer. So we see, so this is climatology, shading is the surface temperature. So we see warm condition in the west. This is the warm pool, and cooler condition in the east, the cold tongue. We have a whole complicated set of zonal currents that flow in the east-west direction. The atmospheric circulation is dominated by the Walker circulation with ascending motion in the west and descending motion in the east, and returning flow at the surface that is given by the trade winds. And also we have this meridional cell describing the Hadley circulation. But in the bottom panel, we actually see something, we go a little below the surface, and first of all, we see that there is this strong current, the equatorial undercurrent, EUC, that really blows from west, that is going from west to east in the subsurface. But the other component of the circulation that is very relevant for decadal variability is given by these little overturning cells, where we have flow moving from the surface to the subsurface away from the equator in the subtropical regions. And then we have flow toward the equator in the subsurface. And then we have this big arrow at the equator that shows the vertical velocity or upwelling along the equator. And then there is a return flow toward the extratropics at the surface. So this these are known as subtropical cells, or STCs, and they connect the subtropical and the equatorial regions and suggest the possibility of remote forcing of equatorial dynamic from the extratropics. And there are in particular two theories that have been proposed for explaining decadal variability. And here we have a more realistic view of these subtropical cells. Of course, the real world is much more complex than a simple overturning. In the real world, the flow is three-dimensional, and these also tend to occur on surfaces of constant density or potential density surfaces. So the first hypothesis for explaining decadal variability, which is known as the V-bar T-prime hypothesis, postulates that temperature anomalies in the subtropics, so in the away from the equator and in the eastern part of the domain, this surface is closer, this isopycnal is closer to the surface, so we can have temperature anomaly that, we have temperature anomalies that move into the water column, reach the equator through the climatological ocean circulation V-bar, and then when they reach the equator, as we can see in this lower panel, they can be brought to the surface by this equatorial upwelling and change the surface temperature. But on the other hand, even if we don't have temperature anomaly, but we change the circulation, as shown schematically in the right, we can actually increase the mass convergence near the equator just because there is more mass being brought to the equator, and then increase the equatorial upwelling. If that is the case, this equatorial upwelling will bring colder subsurface water to the surface, resulting in surface cooling. So while both theories, both hypotheses seem to be feasible, I think is the second one that has been more robustly demonstrated, as the mass convergence at the equator seem to be very strongly correlated with sea surface temperature. In both cases, these changes in the ocean, this variability that we see, are forced by the winds. And so then the question that arises is that what causes these anomalous winds that are responsible for the STC changes? So tropical, we have seen before that even if we have sea level pressure anomaly off the equator, they can also be connected to wind anomalies in the tropical and equatorial regions. So these tropical wind anomalies may be connected to the changes of mid-latitude atmospheric circulation. So influences from the extratropical Pacific can be expected to be important for decadal variability. And one suggested hypothesis is kind of schematically shown here, where maybe we have some internal atmospheric variability, like here shown here by these contours of sea level pressure. It's named the North Pacific Oscillation. And when we have this atmospheric condition, this tends to lead to surface wind that in this case decrease the climatological winds, decrease the heat loss by the ocean, and produce these sea surface temperature anomalies, in particular this tongue of anomalies that go from the coast of California toward the equator is known as the Pacific Meridional Mode, or PMM. And this anomaly can also propagate all the way to the equator, where once they are at the equator, they can affect the atmospheric circulation through atmospheric teleconnection and then reinforce the anomalies of the equator. So this coupled interaction between the equator and the extratropics can actually provide persistence for the anomalies and lead to the longer time scales that can be in the decadal range. So, however, identifying these coupled feedbacks in a clean and unequivocal way, it's quite challenging. So in some recent work, which I have done with some of my colleagues, we have used a statistical approach, a multivariate statistical dynamical approach, which is known as the linear inverse model, or LIM. And we have constructed the LIM over this domain using sea surface temperature and sea surface height as our dominant variable. And then we have looked at the dynamical eigenmodes of this system to try to understand the dynamics of the different modes of variability in the Pacific. And in particular, we have identified this mode of variability, which has a decadal time scale and is characterized by this large anomaly in the Northeast Pacific, again in the subtropics, typical of this meridional mode, and in the tropical Pacific, in particular in the central equatorial Pacific. And so we have termed it as the NPCP, North Pacific Central Pacific mode. And so through various analysis and comparison with other results, independent results, we shown that this mode actually does encapsulate this tropical extratropical interaction at decadal timescales. And in particular, this approach, this LIM approach, also allows to remove this mode or any mode of the system from the data and to see what the impact on the variability is without that mode. So here we are asking how much which fraction of the decadal variability is accounted for by this NPCP mode. So on the top left here, I'm showing just the decadal sea surface temperature variance, and here with decadal is a very broad definition, so I'm taking time scale longer than denser, so going from 7 to approximately 70 years and longer. And then in the middle left panel, we see how the decadal variability would look like if we filter out this NPCP mode. So we see very large changes that are more that are quantified actually in the panel on the right, that shows the ratio between the variance difference and the initial variance. So we can see that in the Northeast Pacific, removing the NPCP mode lead to a decrease of 70% in variance, 80% in the northern tropics, and about 50–60% in the central equatorial Pacific. Of course, we can also, besides the MPCP mode, this system also features eigenvectors or modes, that dynamical modes that represent ENSO. And so we can also ask ourselves what is the impact of ENSO. So if we remove ENSO in the same way that we have done before, we actually see that ENSO has a minor impact on basin decadal variability, except perhaps a minor influence on the eastern part of the basin. As I anticipated before, the NPCP mode appears also to favor the development of Northeast Pacific marine heat waves. Marine heat waves are ocean temperature extremes. They are persistent temperature anomaly, and they tend to are usually associated using amplitude and duration threshold. So a given anomaly will be called a marine heat wave if the amplitude is above, for example, the 90th percentile of in that day or month, and if it lasts for a minimum of few days or months. So how do we assess this? And so in the Northeast Pacific has actually experienced very intense marine heat waves. The most intense and perhaps more influential of them is the one that developed during the winter of 2013–14, which appeared as this big area of really warm water, which was defined by the Washington State climatology, Nick Bond, as the blob. And so we always refer to this marine heat wave as the blob. So these were very large anomaly in excess of 3 degrees C. And not only they didn't only just were limited at the surface. In fact, if we take the average temperature in this box and look at how it evolves in the subsurface, so here we see the temperature as a function of time and depth, we see that these anomalies actually reach quite a ways down, and they can be felt also at 200 to 250 meters. This anomaly didn't stay there, they evolved. So starting from this initial anomaly during the winter of 2013–14, the anomalies extended eastward toward the US West Coast, and then extended southward along the coast and continued to intensify as the ENSO, the big 2015–16 El Niño event, was developing in the equatorial Pacific. And so this whole entire event lasted approximately 2 years, and ecological impact were very profound. So it had very devastating impact, which included mass mortality and starvation of several sea mammals and sea birds. It also included species shift and migration, as we see this, like, for example, the hammerhead shark that we see on the top right. So warm water fish populated the area from the Northeast Pacific from lower latitude, was caused a tremendous habitat destruction. So like the kelp forest, like here we see in the middle panel on the right, were severely damaged or destroyed, and the Hawaiian coral reefs underwent severe bleaching for the first time. And also this warmer than average temperature, also favored the development of harmful algal bloom. They are poisonous algae that caused the closure of several important fisheries like crab. So as I mentioned before, the blob appeared to be associated with the development of these marine heat waves. And so again, we can use our filtering method where we remove this mode of variability from the data to see the effect on this marine heat wave. So this is what we have seen before, where the hatching indicates area that can be considered in a marine heat wave state. So they exceed the 90th percentile for that particular season. And so if we now remove this decadal mode of variability, we see that apart from the very first phase, which could be due to just random atmospheric forcing, the marine heat wave never fully developed. The anomalies were much weaker, and also its severity was very much reduced. Some studies have suggested that also ENSO can really impact the development of marine heat waves in the Northeast Pacific. So we can also remove ENSO instead of our decadal mode and see what it does to these marine heat waves. And we see that things are pretty much unchanged, except along the equator, where the intensity of this 2015-16 event is much reduced. And finally, the last aspect that I would like to touch on is, again, the relationship between climate change and internal variability. So in many studies published on the topic of marine heat waves, marine heat waves are presented as increasing in amplitude, duration, and intensity and severity. The question is this true also for due to the warming, the warming trend, the climate change warming trend? And is this true also for the Northeast Pacific? So here I'm dividing the 60 years of data that I used into sub-period, and I computed the change. So after the trending the data, I computed the change in variance between the second period, 1988 to 2017, minus the first period, 1958 to 1987. And what I find that there is indeed a pretty appreciable change in variance, which is significant at the 95% level. So it means, as indicated by the hatching, which means that it cannot have happened just by chance. So it was a real change. And then again, if we repeat the same analysis with the data without our decadal mode, we see that this changing variance is primarily associated with the presence of this mode of variability. So the enhancement of this NPCP variability appears to be responsible for the intense marine heat wave activity in recent decades. Of course, also the intensification of this mode could result from climate change. So maybe through changes in maybe the ocean structure or changes in the atmospheric circulation. And this is an area that needs further investigation. So to conclude, we have seen, I hope I convinced you, that decadal variability has very important societal impacts. Also, understanding Pacific decadal variability is quite challenging, since its mechanism can be obscured by the strong ENSO variability at interannual time scale, and can also be impacted by anthropogenic climate change. So very difficult to distinguish and separate these different time scales. So it has been, I think, progress has been made in understanding some of the oceanic processes in the tropical Pacific, and also in understanding modes of variability that connects the tropical and extratropical regions. And our current understanding seems to suggest that a large fraction of decadal variability may indeed arise from these tropical extratropical interactions. Of course, a major and very important challenge, is to translate any understanding that we have into skillful prediction of quantities that are important for society. So this is really critical for adaptation purposes, and something that really needs to be, as a community, we need to pursue. And I'm going to stop here. Thank you.
Thank you very much, Antonietta, for this very fascinating talk. A really great dive into the Pacific, and fascinating to see how these long-term processes really impact on the extremes and on both land and ocean.
Should I stop sharing, Ronan, or do you think I should leave the slides up for questions?
I think you can leave the slides up for questions for now. Yeah, just in case. On that note, you remind me that I invite people to write their questions in the Q&A tab found at the bottom of the screen. I see some are coming in already. But in the meantime, I will invite some comments and questions by our discussant of the lecture today, Dr. Anna Pirani. So Anna Pirani is a senior research associate at the CMCC in the Risk Assessment and Adaptation Division. She is an expert on climate risk assessments and climate policies from local to global levels. She has worked on the first EU climate risk assessment and has been a negotiator for the UNFCCC and for G20 and G7, and has played many crucial roles in the IPCC writing and organization. So I would invite Anna to share some comments and some questions on the talk from Antonietta.
Yeah,
Anna,
thanks.
please.
Thanks. Thank you, Ronan. And thank you very much, Antonietta. That was such a brilliant talk. It's amazing just to see, we're basically looking at how the climate system works, how its dynamics are operating, and wouldn't it be a wonderful world if that's what we were studying and not worrying about climate change. But as Ronan said, I'm not going to go into this at all, but I'm here because I'm working in a cross-cutting program in CMCC, which tries to bridge our understanding of climate change and climate variability and the implications for society, of course, not just the impacts, but also the responses that we may take with a view towards going towards a better future or a more sustainable future. So it's clear, from what you're showing us, how this system is working, that all the modes of variability are interconnected. And it's really fascinating to see in your talk, particularly, not just the surface patterns and the teleconnections, but also the subsurface processes that you've been able to diagnose. But as I said, I mean, we're in a fast-changing climate, and so the hot topic still remains, at least for me, what happens to climate's dynamics in this changing climate, and in the context of the climate change negotiations in particular. We're on track towards reaching a level of warming of 1.5 degrees, so the lower bound of the Paris Agreement, and even just tracking current warming and knowing where we are is pretty difficult to diagnose. So I'm curious to know more about how we can assess the effects of decadal variability themselves in climate models, but then how can we also understand if there are changes, if they are, on the one hand, modulating the climate signal, as I think we know they do. You showed that with the hiatus period. But what further changes might be happening? What are the drivers that could alter the variant itself? And your remarkable finding about the statistically significant change in variants of marine heat waves in the North Pacific is perhaps one of the one area that maybe we could discuss a little bit further if possible. So I'm curious to hear your thoughts about this, because the last IPCC assessment report concluded essentially that we haven't, with human-caused climate change, pushed the climate system out of its natural internal variability and cycles. But I'm curious to know what you think from your work, and how to tie the work, which I understand is more based on observational and reanalysis data, how to bring that knowledge, process understanding-based diagnosis into climate models, how to constrain better climate projections.
Yeah. Thank you, Anna. This is a multifaceted question, so I'm going to start from one piece, which is sort of the interaction between internal variability and climate change. And I think the tropical Pacific is actually a very good example for this dilemma that we have, because in fact, I don't know if I can quickly go back to previous slides. I don't know if I can. No, doesn't seem to let me go back. So what we see in the observations, which are short, and so there are large uncertainties in the determination of the trend, but we see that there is a muted warming signal in the Eastern Pacific, which actually, depending on the period you consider, can be cooling, and extra warming in the Western Pacific. So the zonal sea surface temperature gradient is actually increasing in reality. practically no models show that, except maybe for a few high resolution model that people are trying to explain this improvement with the processes that can be captured by higher resolution, especially in the South Pacific. So this opens the question of is this cooling trend in the Eastern Pacific that we are observing just a part of internal variability that the model are not in the right phase to capture, or I think studies have shown that the model may underestimate decadal variability, and so they don't see this change, or is actually a true climate change signal which the model reproduce wrongly. So this, I think, we need to proceed probably with different tools. I think we need to devise some clever approaches. A very hard question to address, and because we don't have the tools. So we have short observations, we don't know how the trend is going to look like, and so we are just trying different approaches, and also we cannot trust the model to tell us what is happening. So, but I think one important thing to bridge observation and models, to bridge, these two time scales, and also I think to move forward, is really trying to apply diagnostics similar to what we do in observations, to apply them to the model. So I think to date, the model assessment, since we have all these terabytes of data for each CMIP experiment, tend to be basically limited to the surface. So people say, okay, does it have a realistic pattern of PDV, of sea surface temperature? But I think we actually need to really challenge the models and see whether they have similar processes. So the slim approach that I described is not, of course, the only way, but could also be developed for models and see if actually model have the same feedbacks that we detect in the observational system. So I think that will at least help us gain a better sense of how much we can trust the models on the historical period, and then use them to see what we can expect in the future. Because then when you understand the processes, and so, for example, the adjustment is due to ocean dynamics. So if in the future the stratification increases, we know that this may happen faster. So we can extrapolate of what to expect in the future when we know what are the ingredients in the real world that matter, and if they are correctly captured by the model that we use. So I think I would start from there, and then meanwhile, I think there was actually a 10-car and hackathon to look at different methods for estimating the trends. And I think we should continue with those exercises to really try to understand which approach or which estimate is maybe more robust, to have an assessment of what the observed trend is.
No, thank you. That's very comprehensive. And we haven't got much time, and there are some really good questions in the chat on the question answers.
Okay.
I mean, there's one I'm just going to pick up because I would be tempted to ask, what about initialization? And, the use of decadal initialized predictions, for example, to diagnose the immediate climate change periods, for example. But Panos was asking a question related to that, and maybe I leave that to Ronan to moderate the questions. Thanks.
Thank you, Anna. We can indeed begin with Panos's question. Should one expect that initializing upper ocean heat content in the equatorial and subtropical Pacific could provide decadal predictability for the atmospheric circulation? And then he asked, or perhaps it's preliminary, the chaotic atmospheric variability that drives the NPCP.
Yeah, so I think the heat content is very important. Although I don't do prediction myself, I think that there is actually a paper that used by Libby Barnes group in the US So she used artificial intelligence method, and they were doing exercises of decadal prediction, and they used quantities similar to what I use for my limb, so sea surface temperature and sea surface height, or equivalently heat content. And they were able to get some skill in this decadal prediction. And then, since Libby is very interested in explainable AI, so she's the one who is pushing this approach, so they looked at the heat maps that were associated to the skillful prediction, and they, sure enough, found these areas. So these areas in the Western Tropical Pacific where we see that there is enhanced int content or reduced its content, depending on the phase of the decadal variability. Those areas emerged as critical for the success of the algorithm. There is also some work by Jerry Mill, who I think paper was published in 2016, where he also showed how this heat content seemed to improve the detection of the phase transition of the Pacific decadal variability. So I think those definitely is important to include in your system.
Excellent. Given that we are at the Euro-Mediterranean Center of Climate Change, and I know many people online will be interested in perhaps processes closer to home as well, I will take a quick detour into the Atlantic because there are two questions on the Atlantic. The first from Dario, whether interbasin interactions, particularly with the Atlantic, can also play a role in modulating the variability in the Pacific. And similarly from Simona, there's been evidence recently that in 2023 in the North Atlantic, there have been long-term, very large-scale extreme temperature anomalies. Could they have a similar nature to what we've seen in the Pacific, for example, the blob? And do we have any hope of using perhaps some of your analysis and applying that to the Atlantic?
Okay, so let's start with the first question. I actually used the same limb methodology. I didn't do the calculation. I was in collaboration with a young colleague. So we constructed a limb that had the Pacific domain and the Atlantic domain to try to understand the coupling between the two basins. So again, in the limb, it's when we have the mathematical operator, we can play with it. And so the element of this operator represent feedbacks between the different elements of the climate system. So we can, in fact, remove the feedbacks between the two basins and just leave each basin operating with their own dynamics. So, and what we found, so the question is very relevant because I think people are talking, and in fact, also the cooling in early 2000 that I talked about, some people attributed it to possibly effects of the Atlantic. So what we found is that the Atlantic can actually have an influence on the Pacific at interannual time scale. However, at decadal time scale, the Atlantic could enhance decadal variability in the Pacific, but only if the effect of the Pacific on the Atlantic is disabled. So the way the two basin operates is that the Pacific induced anomaly of the same sign, the Atlantic induced anomaly of the opposite sign. At decadal time scale, this negative feedback, I think, tend actually to reduce decadal variability in the Pacific. So at least that's from my own personal experience. And then in terms of the North Atlantic, there have been some very nice study on the North Atlantic. So the tropical Atlantic can be affected by ENSO, that was there in 2023, but in the North Atlantic, it looks like the patterns seem to be typical of the Atlantic multidecadal variability. So the studies that have been published on this topic, very nice studies, they have shown that indeed there was a component of internal variability. But what they found is that the strong increase of the ocean stratification with climate change made the anomaly much more severe. So there was a strong atmospheric forcing, which itself could be affected by climate change, but by itself would not lead to the extreme character of these anomalies. I think the extreme character emerged from the fact that you had a strong stratification, so the heat was really mainly confined in this very thin upper layer. And this stratification seemed to be the result of climate change through a progressive transformation of the upper ocean. I don't know if this answers the question.
Thanks, Antonietta. I'm looking at the clock and I wonder if you could say 2 brief words, if possible, on tipping points, because there's an interesting question from Paolo on the fact that tipping points are becoming more on sort of an impact, but the phenomena occurring within the next few decades rather than centuries.
Okay, so well, I think we have seen pretty dramatic shifts in recent years. And I think both in, well, in the Atlantic, this big jump in temperature in the Atlantic, it was really unexpected, unprecedented, and I think we're still scratching our head how, that could happen. So it's clearly, so whether we can actually move to a different state, I think that's, I'm not sure if we can say that from now, because I think there has been a return to kind of to some degree to the pre-existing condition, for example, if we think about the North Atlantic. So I don't think we have seen enough, but I think it's also conceivable that if you consider, so for example, in the context of the limb, you have all these modes of variability that interact to one another. They are not orthogonal. So that if we combined with climate change, if you can also have a superposition of this mode, which is with the right phase, you may have some big changes and which could maybe be seen as tipping points.
Well, it's a testament to how interesting your topic and talk was, because we are right at the end now, and there are still some potentially interesting questions and themes to talk about: tropical cyclones and ENSO dynamics. Unfortunately, we have to close the meeting now, close the lecture, but I invite anyone else to contact you perhaps afterwards.
Yes, please. I think I would be very happy to be contacted via email for any additional questions, and I would love to discuss more.
Excellent. Well, in that case, I will thank all the participants and for taking part today and for their discussions. Anna Pirani for the very interesting multidisciplinary discussion earlier on. And of course, finally, Antonietta Capotondi for this fantastic lecture. Thank you very much.
Thank you, everybody. Bye-bye.
Thank you. Thank you, Antonietta. Bye.